Okay, good afternoon, everyone. Today we have Detlef van Vuuren talking at the CLEX seminar series. So Detlef van Vuuren is a professor at the Faculty of Geosciences at Utrecht University and a senior researcher at the PBL Netherlands Environmental Assessment Agency, where he leads the image modeling team, which stands for the Integrated Model to Assess the Global Environment. Professor Detlef has worked on a number of integrated assessment models and has coordinated the development of the RCP scenarios using the IPCC reports. He's an author of several IPCC reports. He participates in international programs, including the Earth Commission, the Global Change Budget, and the Integrated Assessment Modeling Consortium. Professor Detlef is a member of the Royal Academy of Sciences and Arts in the Netherlands, and this year he was listed the 4th most influential climate scientist in the world. So today we have Professor Detlef we're talking about the modeling framework and discuss the RCP SSP scenarios with us. It's an immense pleasure to have Professor Detlef talking at the CLEX seminar series. So I'll just open the floor to you and you can start the seminar. Please put your questions in the chat.
Okay, thank you. Yeah, good afternoon, good morning here. And it's a pleasure for me to be here. So my talk is about scenarios. And scenarios are used as a tool, as a scientific tool to connect different sciences, and I come back to that. But they're also obviously used for policy making. And one important reason why we need scenarios is also the times where we're in. We're in for climate in extremely challenging times, where we on the one hand have overwhelming evidence of crisis. For instance, just look at the increasing greenhouse gas emissions that continue to increase even after the Paris Agreement. And at the same time, we are in a world with great ambitions. The Paris Agreement was signed in 2015, and we promised to the world that we want to keep climate change well below 2 degrees and preferably below 1.5 degrees. And there seems to be this enormous tension between these two worlds. And the question is, what is needed to change course? And what automatically that it actually means that you're asking yourself what could happen in the future. And that's actually a really difficult question to be looking into. If we want to know something about the future and long-term futures like we need for climate change, we need to have insights on population, on things like socioeconomic development, on technology, how fast will the cost of solar cells decline further, or what will happen to coal prices. We need to know something about demand for food and energy and water. And we even need to know how environmental problems might feed back and influence the other factors. And not only do we need to know these things, but we also need to know them at different scales. That's something that might happen in Europe. A policy on bioenergy might have influence in South America, if South America would be exporting that bioenergy, but also for different time periods. For CO2, it's very clear it's going to influence the climate for centuries, but also a choice on a power plant typically involves 40 years because the power plant is going to be there for 40 years. We need to know the interactions. Yeah, again, take the example of bioenergy. A choice on bioenergy for climate might influence, for instance, biodiversity because you need land. And then everything is uncertain as well. And so we also have to account for these uncertainties. Now, at some point, it becomes really too hard to capture everything by head. And that's why we have these model-based scenarios to help us trying to explore the future. And it's quite important to realize that this is not meant as predictions. We simply don't have the capacity to predict political systems into the future. And the next US election can change the world quite dramatically. But it is a kind of exploration of the future. Compare it with map making. And somehow we're trying to understand as best as possible how different futures may evolve and what we would encounter on that way. And so there are elements of the future that we can reasonably describe in models to support scenario making, like physical entities, the physical system, the physical climate system. There are also parts of the future that are reasonably well described by models and mathematical equations, like rules or laws, economic systems. And then there are things that we really are difficult to describe in mathematical equations, like beliefs and culture. And so if we are using model-based scenarios, we're actually combining two tools. One is we use models where it's possible to use mathematical equations to better understand relationships. And at the same time, we use stories to describe those elements where actually words and stories better can capture the uncertainty than models can. Yeah, and then we develop scenarios. And those scenarios are, as I said before, explorations of the future. They can help us understand different pathways in the realm of the possible, but they can also help us to understand, for instance, what are really unlikely events. If we are going to develop scenarios for climate change, they need to describe the full chain of climate change. And so this starting from drivers to energy, drivers like population and economy, to the demand for energy and land use, to the consequences for emissions. Subsequently, they also have to describe what it means for concentrations, climate change itself, and finally impacts. In climate research, scenarios have another very important role, which is actually connecting different research disciplines. And we have somehow really nicely divided the research into socioeconomic modeling, integrated assessment, which describes the first three boxes. Then we have climate models, physical models, chemistry models that describe the Earth system. And then finally, we have the impact community looking into climate impacts. The scenarios are a very important tool where we bring information from one research realm into the second and into the third. And even IPCC is organized exactly in the same way, with Working Group 3, Working Group 1, and Working Group 2. And so scenarios are not only a very important tool for us to describe possible future change, it's also an important vehicle for information exchange between these communities. And now just start from this system at the very end, impacts. Now, impacts are a function of climate change. The more climate change we have, the stronger the impacts that we expect. But they are at least as strongly influenced by socioeconomic developments directly. And just compare the Netherlands and Bangladesh and think of a 1 meter sea level rise and what will happen to these countries. And one of those countries will be able to adapt, to invest further in dikes, to adapt to climate change. For the other country, it's much more difficult given the lack of resources to do so. And so, again, there are two very important factors: the amount of climate change and the socioeconomic conditions. And in developing the SSP scenarios, this was actually what we used. We said, okay, if these are two critical elements, let's put them on the two axes of a matrix. And then think of the future as being uncertain in terms of the level of climate change and being uncertain in the level in the socioeconomic conditions of this world. And then you get a matrix of uncertainty of things that could happen. But then for that climate axis, we already had something, which was this forcing axis that we already developed for the RCPs. I come back later to that, going from 1.9 watts per square meter, comparable to the 1.5 degree target, to 8.5 watts per square meter. That's the highest scenario that we developed at the time. But for the socioeconomic pathway axis, we didn't have anything. And so there we needed to develop something. And so if we are going to talk about future climate change, we might be talking about future climate policy. These scenarios need to be relevant for climate policy. And so we thought of two critical axes if we are talking about climate policy. One is adaptation and the second one is mitigation. And we can imagine worlds where it's relatively easy to mitigate and worlds where it's relatively difficult to mitigate, and just the same for adaptation. And that we thought was a useful way to then explore the future. And we can potentially think of situations where it's relatively easy to mitigate and relatively easy to adapt if the population growth is relatively slow, if the economy develops relatively fast, so people have resources. If technology development is relatively fast and people also cooperate, that might be a situation where it's easy to mitigate, easy to adapt. In contrast, if we have strong population growth, if the economy is not developing very fast, if there is no cooperation in the world and people need to use their own domestic resources, like for instance in Asia, coal, that might be a world where it's relatively difficult to mitigate and difficult to adapt. And that's what we then made the Ssb3 storyline. We sat down with about 60 people at some point in Denver and tried to elaborate further what would be the stories underlying each of these points on this second matrix. And that resulted in the descriptions of the future. The Ssb1 world, I already described a bit, is a story about green growth. And we indicated all kinds of elements that could be part of that particular storyline. And we did the same for the Ssb3 world, where is this regional rivalry world, where there's competition among regions and slow economic growth. And we did the same also for the other scenarios. The Ssb5 scenario became the fossil fueled development world. Ssb4 is a scenario where we emphasize inequality. And then we also developed a scenario in the middle that had more or less medium assumptions for everything. That could be used if people simply were interested in exploring a medium scenario. And so after developing these storylines, we could start to use models to elaborate these scenarios further. And the first step was actually to elaborate population and income. We did it with the demographic team at the EASA and the economic team at the OECD. They used their long-term models to find out population developments and economic developments consistent with these storylines. They put assumptions into these models that were consistent with the storylines. One of the most critical here is actually education, which influence both future population development and income. And they collaborated on that, resulting in these scenarios where you see on the right population increasing forever in the Ssb3 scenario, but combined with a relatively slow economic growth path. On the other end of the spectrum, we have Ssb1 and Ssb5, which have a relatively low population development. Population increases to mid-century to about 9 billion people, but then peaks and comes back to about 7 billion by the end of the century. And both those scenarios have a relatively fast economic development. Yeah, the next step was actually to bring this information and the storylines into this integrated assessment models. And then the integrated assessments could first of all use these quantifications, but then they also had to translate the storylines into things that go into the model. So for instance, a model, this is actually the image model, the one that we use in our team. But we have a description of agriculture and energy. In both systems, we need to make assumptions about how fast technology develops. Yields in the case of agriculture, the individual energy technologies in the energy system. And we could base our assumptions on the storyline. If the storyline emphasized relatively strong technology development, and then for all the technology assumptions that we have in the model, we choose relatively optimistic values. And we could do the same for the Ssb3 scenario, where we then took pessimistic values. So this allowed us to make consistent assumptions in different parts of the system. And this is, for instance, showing you a graph from the image model. This is global energy use in different sectors, where you see that in the Ssb2 scenario, energy develops further over time, and especially electricity use continues to grow. And using the model is actually working in 26 world regions, but I'm showing you only global results. We could also elaborate how energy supply would look like in those scenarios. And you see here with the colors black, green, that's greenish type color, and brown, the use of oil, gas, and coal. In the Ssb3 scenario, consistent with the storyline, also in the future, the energy system is dominated by fossil fuels. In the Ssb1 storyline on the left, you see that renewables rapidly come into the system. There are also quite large differences in energy demand between these scenarios. These are all scenarios without climate policy. We simply didn't, we know that climate policy is there, but in these scenarios, we assume that the climate policy is not strengthened further because we want to develop these baselines first. And in these worlds, we see that there's a further increase in energy use. Fossil fuels continue to be important, and there's also increasing greenhouse gas emissions. So models like Imc then can also do the same type of thing for the agriculture system. Here we see demand for crops for human consumption, but also for animal husbandry, and then also the consequences for that in terms of grass and crop feed production. And this has to be fulfilled by land. And so we also calculate future land use. And in the image model, this is actually done on a 5 by 5 minute grid. So we calculate current land use, and then based on some rules in the system that, for instance, assigns production to those grid cells that are best able to produce, we can make maps of the future. Yeah, other rules are, for instance, agricultural land is likely to be near water bodies or expand near existing agricultural cells. And you see in this future that actually there's a further expansion of agriculture area in Africa, mostly at the loss of tropical forest. In the north, you actually see some reforestation. This is Ssb2 scenario. And in 2100, that trend simply continues. And then we can contrast that with the other scenarios. I already indicated that the Ssb3 scenario was this scenario where there was continuous population growth. And now we see the consequence in terms of further decrease of tropical forest, especially in Africa and in this case also in Latin America. Ssb1 is the scenario where population peaks in 2050 and then comes down, where there is relatively rapid technology development, where people are relatively environmentally aware. And there you see the contrast. Actually, there's a small gain of tropical forest compared to even today. With an energy description of the energy system and of land use, it's relatively easy in the model to calculate the consequences for greenhouse gas emissions. And so on the left, you see the greenhouse gas emissions in the Ssb2 scenario, at least as it was some years ago in our model. And on the right, you see the development for the Ssb scenarios, Ssb1 to Ssb5. So just focus for a second on the Ssb2 scenario here again, which is shown on the left, because from then it's relatively easy to start thinking a little bit about the climate consequences. In the model, this is done using a small climate emulator called Magic, but you could also obviously use the relationship shown on the right, which is the plotting of cumulative CO2 emissions from large climate models against temperature. And as some of you might already have seen this in the Working Group 1 report, a linear relationship emerges, referred often to as the TCRE relationship. And yeah, you can then fill in the cumulative CO2 emissions you see in the Ssb2 scenario, combine that with the already existing cumulative emissions, and you can estimate how much temperature rise would emerge from that, which would be about 3 to 5 degrees. Yeah, you can combine that with the work of Working Group 2 that have plotted possible impacts of climate change against temperature. And you would see in this case that we are all in the area of high risks. Yeah, in this graph, which is taken from Working Group 2, on the x-axis are different types of risks, going from the left, risks to unique and threatened systems like coral reefs, and on the right, the risk to large-scale discontinuities, like for instance the slowdown of the Gulf Stream in the Atlantic Ocean. And yeah, the colors indicate high risk, indicated by purple, or no risk indicated by white, and everything in between. And with 3 to 5 degrees, according to Working Group 2, assessing the literature, we're in high risk for all these different risk categories. And we knew this because the world already had decided we want to be well below 2 degrees, and preferably at 1.5 degrees. And so we can now read the graph in a different way, and to know how much CO2 can we still emit to be consistent with these targets. And then you end up with about 1,000 gigatons CO2 for well below 2 degrees, for the interpretation of well below 2 degrees, and with about 400 gigatons CO2 if you want to stay below the 1.5 degree target. Now, and both are very uncertain. You can see that there's uncertainty among the climate models indicated by the pink plume, and as a result, there's also uncertainty in these carbon budgets. And these carbon budgets are relatively small. I can illustrate that directly, for instance, by comparing them to the amount of CO2 that is already emitted since pre-industrial time. And then, especially if you look at the 1.5 degree budget, we simply have a very small amount of CO2 still remaining compared to what is already emitted. But this is also true for the well below 2 degree target. But there's a different way that we can show how small this carbon budget is, which is simply by plotting it on the graph of projected emissions and historical emissions. And so this is the line that you would follow if you go from now linearly down to 0 and emit 1,000 gigatons of CO2. And so instead of the historic trend of increasing emissions slowing down the last few years, it has to go down really rapidly and breaking completely with the past, and be at about 0 just after 2060. And it's about 45 years that you have to be at 0, which is challenging because more or less everything we build, like factories or power plants, are meant to stay for at least 40 years. So this scenario would more or less mean building everything today CO2 of greenhouse gas free, carbon neutral globally. So not only in the Western world, but also in Asia, also in developing countries, which is not really happening yet. And then for the 1.5 degree scenario, you can do the same thing. And then you have to be at 0 in about 18 years. Yeah, that means already not building anything anymore that emits CO2, but also prematurely close down some of the existing infrastructure, because the existing infrastructure is already going to emit, if it reaches the end of its lifetime, 650 gigatons of CO2. So these are very challenging scenarios. They're absolutely not impossible, and I will show pathways further, but just to illustrate that we have brought ourselves in quite dire straits. Yeah, so there is luckily a few things that can help us a bit. One of them is the existence of negative emissions. There are ways that we can take CO2 from the atmosphere, like reforestation or bioenergy with CCS, but also direct air capture, taking CO2 directly from the atmosphere and storing it underground. There are also nature-based solutions like increasing carbon in soils, and that obviously can help to soften the transition a bit. And that can also happen for the 1.5 degree scenarios. But we have to realize we can't use that indefinitely. First of all, if you do it like shown in this graph, then you will have a temporary overshoot of the temperature target. You will emit too much CO2 first, and that automatically translates in a temperature overshoot. But secondly, many of these options that I just mentioned, reforestation or bioenergy, will require land. And so that might involve difficult choices with respect for instance, biodiversity protection. And if in the worst case, even possible impacts on food production. So the potential is limited. And in the literature, there are estimates about maybe 100, maybe 400 gigatons of negative emissions, net negative emissions that might be possible. That is helpful, but to remember, when I showed the positive scenario, that was 4,000 to 5,000 gigatons of CO2 emissions under an Ssb3. If you want to go to a 1.5 degree, 400 gigatons carbon budget, and then we have to first of all avoid 4,000 gigatons of positive emissions, and then we have potentially 400 gigatons of negative emissions that can help us doing that, and might be important, but the big story is simply avoid positive emissions. Now, I have been creating very simple scenarios so far with just drawing lines, but we have obviously these computer models that can help us a bit. And with some computer models, we can calculate optimal scenarios, cost optimal scenarios for different targets. We can also play around with assumptions and allow more nuclear or be more optimistic on PV. And we can also make different assumptions about policies being emergent over time. And so we can create a huge cloud of different scenarios, but they're all bounded by the fact that they need to be either within the well below 2 or the 1.5 degree target. And that means that we have some flexibility in pathways, but at the same time also quite some limitations. They have to be within the carbon budget. And so I'm showing some of the graphs that might come out, and we get a funnel, but also with a limited width. And yeah, some other parameter that we can still play with are the non-CO2 emissions. I've focused pretty much on CO2 so far, but non-CO2 is also part of the game. And by, for instance, reducing non-CO2 stronger, you might create a little bit of additional room for CO2. Yeah, that means that you can run models really a lot and create some indication of when do you expect emissions to be at 0 for different targets. For well below 2, that's the upper set of bars. And most scenarios show that for CO2, emissions need to be at 0 somewhere between 2060 and 2080 globally. And for greenhouse gases, this is slightly later, simply because it's relatively difficult to reduce non-CO2 emissions to 0. It's relatively easy to halve them, for instance, but it's really hard to get them to 0. And that's typically the moment that we reach 0 emissions is about 10 to 15 years later for total greenhouse gases than for CO2. And that black dot, by the way, is the result of that linear line that I showed you earlier. Now, for 1.5 degree, that means that we have to be at 0 even earlier, and scenarios would indicate a range of somewhere between 2035 and 2060. So the net zero target is less certain if you want to reach a climate goal consistent with Paris than a carbon budget. A carbon budget is a much more strong direct relationship between those goals. But the nice thing is that it sets a relatively clear point at the horizon. So for policymakers, if you indicate that we have a net zero target, it really helps to think of, okay, net zero means going to 0. So everything has to become 0. Transport systems have to become 0. and electricity has to become zero, and buildings have to become zero. And so natural gas, that, for instance, in the long term, doesn't fit unless it's combined with carbon capture and storage. So it has the advantage of forcing everybody to think of, okay, can we think of these systems in a way that they don't produce greenhouse gas emissions? They also have a disadvantage if they are interpreted as something a few decades ahead, while, as we know from the carbon budget, you wouldn't get to the climate goal if you only would meet the zero target in that particular year. You already have to reduce emissions rapidly on the short term. And so we need to communicate that as well. But the emerging consensus now is that if we would aim for net zero globally around 2050, we would be more or less consistent with Paris if you compare that for the well below and the 1.5 degree years for net zero. So how do we get there? Again, we can use computer models to show possible pathways that are consistent with these targets. And then we start to use the models that like Imc, the integrated assessment models, a little bit in the opposite way that I showed before. Earlier for the baseline scenarios, we started with assumptions and then build it up. In this case, we start with the goal, staying within 1.5 or within the well below 2 degree target, and calculate what are the consequences for energy systems and for land use. Now we know that in the model, then you would get measures taken that reduce demand by increasing efficiency and lifestyle change. We get options included that change the system to much more climate neutral energy supply. And there we really benefit from what happened actually over the last decade, where renewables became at par with cost compared to their fossil fuel alternatives. The cost of solar cells went, for instance, as shown on the graph by the right, on the right, went down really dramatically. While maybe 10 years ago, you would say that solar cells are a way to reduce emissions, but unfortunately relatively expensive. By now, they're competing in cost with fossil fuel alternatives. The same for wind power. And then we also have the option of CO2 removal. Yeah, and so we will use then the models again and to get some insight. So here we have the Ssb3 type of scenario again, and the projected emissions in different categories. And note that blue is the energy sector is mostly electricity supply. Then in gray we have the second important cause of emissions, which is non-CO2, and for instance in in purple we have the emissions coming from industry. Globally, actually, buildings is a relatively small sector. In most developed countries, temperate developed countries, it's a much a larger part of the total sum. Yeah, and then that's consistent with an energy system as shown here, with blue being fossil fuels, green renewables, and yellow bioenergy. And so now summarizing that on the right, only for 2050 and 2100, it's the same scenario, but I just wanted to concentrate on those years. And then showing scenarios that are consistent with the 1.5 degree target, the 400 gigatons of CO2 budget, and then ask the model, can we design a system that is consistent with that? And the model is actually showing that there are pathways that can do this, but everything needs to change. And so we see on the top end that this is a scenario where we allow carbon capture and storage, also in combination with bioenergy. And as a result, this model, this scenario shows that we can meet the target. It is reducing emissions rapidly, but it's also using negative emissions, the light blue, to, by the end of the century, compensate for some emissions and come back to the carbon budget. And also it's rapidly changing the energy system. But because of the negative emissions, even by 2100, in combination with CCS, there are still some fossil fuels in the system. But we can also indicate to the model that CCS might not be as available as under our default assumptions. We assume that renewables might develop faster, and then we can find a scenario which also meets the 400 gigaton CO2 budget on the middle, but mostly with renewables. And we can also design scenarios where we are more optimistic on energy efficiency, lifestyle change, and also those can meet the 1.5 degree target. So what do we know? Basically, if we look a little bit from a distance to all these scenarios, we know that there have a few things in common. So first of all these scenarios need to limit demand. If demand is continuously increasing, there's no way that we can ever meet the target with just supply side measures. And that can be coming from efficiency and lifestyle change. All these scenarios profit from the fact that renewable energy is relatively cheap. So even the CCS scenarios, renewables plays a big role simply in the short term, also because of their competitiveness. Because of the relatively ease that we can decarbonize the electricity system, electrification plays a big role as well. And so in all scenarios, you, for instance, see transport being mostly on electric vehicles, profiting from the ease of decarbonizing the electricity system. And then there is a need for other options also in the renewable, in the electricity system, because there needs to be some form of stability there as well. So there needs to be something with system integration, possibly some options to ensure that there is backup power like CCS, bioenergy, or nuclear. And in those energy demand sectors where electrification is not very logical, there needs to be supply as well for heat, which could be coming from hydrogen, CCS, or bioenergy for certain applications. Think of, for instance, air travel. Then reforestation plays a role in almost all these scenarios. CO2 removal is an element, sometimes a bit small, sometimes a very important role, like the first scenario that I showed. Then non-CO2 needs to be reduced, partly by technical measures. But it should be noted that at the moment, we are only identified measures for to reduce non-CO2 by technical measures to about half, which means that scenarios that do have lifestyle change as part of their storyline can benefit heavily if diet change is part of that, because most of these non-CO2 emissions, especially the remaining ones, are related to meat consumption, which means that if you are able to reduce meat consumption, you make this puzzle quite a bit easier. So this is a graph that I showed before. These are these SSP scenarios as they were developed as baseline scenarios, so without climate policy. And now we could use the models, and I've shown you what comes out of it. If you start to meet climate goals, and you, in this case, we have developed for each of the SSPs scenarios that would meet the well below 2 degree target, and you see that the energy system completely changes. It's reduced in demand. There is a substitution of fossil fuels by renewables, possibly also with nuclear power, possibly also in combination with fossil fuels and CCS. But a major change in this energy supply. But also in land use, for instance. Here we have two different options for two different scenarios. One emphasizing reforestation, which was on the left, and which can be part of the solution. In other scenario, we calculated that bioenergy was part of the solution, which is the scenario on the right, where red cells are scenarios used in the model for in the future for bioenergy production, and green cells are still reforestation cells. So this is the matrix that I really showed at the beginning of our talk, with the on the one axis the forcing level, on the other axis the socioeconomic conditions, and I was indicating that this is two major uncertainties, and that we need to start exploring how different cells here look like. So we did that, and one consequence is that actually we could remove certain cells. Under certain storylines, we don't go as high as 8.5 or 7 watts per square meter. In certain scenarios, it's really not possible to go as low as 1.9 watts per square meter. And so we do have now scenarios in most of these cells. The next step was that we wanted to use this also in different climate communities, climate research communities. And so we wanted to hand over these scenarios to the Working Group 1 CMIP world. And running so many scenarios is something impossible with climate models, as you know better than I do. And so we selected scenarios, and we assumed that to some degree, certainly for the high forcing levels, the differences in socioeconomic conditions are not really seen by the climate models. These scenarios have differences in land use patterns. They have some differences also in air pollution that are things that also picked up by climate models, but the most important thing is that they differ in terms of forcing of greenhouse gases, and which will dominate. On the low side, also there, we assumed that the greenhouse gas forcing would be the most important variable to look at. There you might question whether that assumption is correct. But based on that assumption, we could take one scenario from each row and hand that over to the climate research community. And that's what's done for CMIP6. And we selected scenarios and gave them to CMIP6 to calculate and to have climate consequences, which we then could bring back to the Working Group 2 community to combine climate impacts and socioeconomic conditions to make estimates of impact, but also give back to the Working Group 3 community to calibrate our simple climate models and for us to explore different futures with climate feedbacks. So how does this compare to CMIP5 and the RCPs? So when we developed the RCPs, and this is already back in 2008 when this started, we wanted to do this relatively fast. And so because it was mostly focused on CMIP5 and on the climate models, we decided at the time that we didn't want to waste too much time developing new socioeconomic pathways. And so we took from the existing literature, existing scenarios that would make a range in terms of possible forcing levels. And that created the RCP 2.6, 4.5, 6, and 8.5. But we didn't send at that time the socioeconomic pathways with them because they were taken from different publications and had different assumptions on socioeconomic pathways, but they were not consistently made. And so one big difference is that we now have a set with forcing and socioeconomic descriptions. The other thing is that the SSPs are more modern, and so they are created a couple of years later. They have a better description of air pollution, of land use, greenhouse gases, emission climate policy starts a few years later. By now, by the way, the SSPs are also getting outdated again in terms of assumptions for climate policy. And so they have, I guess, most of them have climate policy starting in 2015. That's a bit hard nowadays. We have much more modern scenarios as well in our own database, but obviously the whole cycle in CMIP takes quite a bit of time handovering, and the handover of climate scenarios to the Working Group 1 community and then to the Working Group 2 community. Yeah, so in my final slide, I would like to see where we are now in climate policy compared to the scenario, the whole discussion that I just gave. So this is actually from the presentation so far. We see the Ssb3 or no climate policy scenario going up in gray, and then we see the pathways that we discussed for 2 degrees, 1.8 degrees or 1.5 degrees. It's all kinds of scenarios that would meet those goals. And now let's focus only on that first part, the 2015, 2030 part. So I'm going to blow up that part. And you see the same pathways, but now I've added 2 scenarios. We calculated the impact of the current pledges by countries as part of the Paris Agreement, called NDCs, Nationally Determined Contributions. And we have made a huge database of all current policies in different countries and assessed what those would mean. So for compared to baseline, for the 2 degree and the 1.5 degree target, you would need to have these either 60% emission reduction by 2030 or 40% emission reduction compared to baseline in 2030. Our estimate is that for the NDCs, you get about 70% emission reduction. And for the current policies, this is about a 9% emission reduction. So this is the big challenge that is going to happen in the next few years. The designers of the Paris Agreement had already imagined this, and they designed something called the stocktake process. And that means that countries now should be comparing what they promised, what they're implementing, to what is actually needed, and then try to encourage themselves to have stronger commitments. That process will work, obviously, but I'm not sure how whether people have realized enough how fast this needs to happen. If you want to be consistent with the 400 gigatons of the 1.5 degree target, simply the current emissions are about so the budget is only 9 times larger than the current emissions. And so if we continue to emit the 2021 emissions every single year from now on, in 9 years, we have actually fully exploited the budget. So this stocktake process needs to be extremely fast, and even for well below 2, negotiations need to happen fast. On the one hand, so this is the pressing thought. On the optimistic side, if you would go back 10 years and think of how challenging this would be, you have a much larger carbon budget, but things have completely changed in terms of the cost of renewables and the attention that people have for climate policy. And so there's also a positive thought as well. That's where I would like to close and open the floor for questions.
Thank you. Thanks for your talk. We do have some questions coming in the chat. Please put the questions in the chat, and if you prefer to speak, just raise your hand and I can see if I can find you. So we do have a question by Sarah Taxek. Is country-specific data assumptions available for the AM input and output data?
Yes. So on the we have something called the Imc Database. There we collect output of all models. We make it there available for 5 or 6 world regions, simply because we need to harmonize it across models, and every model uses its own regional definitions. But if you approach modeling teams individually, most of them are obviously willing to share their regional output. And now in the case of Imc, we calculated 26 world regions. So US is a region, China is a region, but on the other hand, Western Europe as a whole is a region, and Australia is combined with New Zealand. But that information is available from us, and we share it on our website. You can also get more modern scenarios directly by email. So yes, it is available.
Thanks. Next question by Dipayan. Do changes in energy source affect land use patterns directly?
And the change in energy source affects the land use patterns directly, is the question. Yes. Yeah, so that's absolutely true for bioenergy. And this is a concern, and it's also a reason why it's interesting to use integrated assessment models, because we can explore different options here. I'm a little bit more optimistic than the situation as expressed by many NGOs. I think there are scenarios where bioenergy will fit, assuming that yields improve in a way that they did historically, assuming that you can somehow steer bioenergy to places where you would like it to be, and so policies, environments can be effective. But it's a concern as well. If those two conditions don't exist, bioenergy can also be causing quite some harm in terms of increases in food prices or loss of biodiversity. The other forms of energy also require land. On a global scale, this is not the biggest issue, but locally, obviously, certainly in densely populated countries, the land required for solar cells or wind is an issue, but it's on a global scale, not a big thing. Yeah, and hydropower, indeed. Hydropower has a relationship also with water consumption, and is slightly more demanding in land use, but it also has this, but then it goes via the water availability.
Thank you. Another question by Sarah. What are the best examples of IAM and climate scenarios informing spatial planning, in your opinion?
So in Europe, there are more detailed models that are used as well for more land use planning. For the global scenarios, we do provide land use scenarios. I think they're used heavily also in research because it's an important factor as well, certainly at the local scale, to look into biophysical impacts of climate change. It's also very useful to explore consequences for land use, like I've shown for tropical forest. But given the resolution that we have in our models, you have to be also a bit careful interpreting our maps directly. As I said, in our case, it's determined by all kinds of rules that we set there, as assuming, for instance, land use is mostly going, agriculture areas mostly going to high yield areas. In reality, there are all kinds of policies that determine land use on a country level that are not represented in the model. So just indicating that for the global scenarios, land use is a very important outcome, but you have to be a bit careful interpreting that directly for land use policy. But on a country and a European level, we do see more dedicated models.
Thank you. The next question by Scott Power. He's congratulating the talk, and he's asking, NDCs don't include recent pledges, do they? Example, pledges made at Biden summit.
Yeah, correct. So the NDCs that I showed here were more or less the situation in 2020. I think I had on the slide, I'm not sure, take the situation about a year ago. So since last year, there were several countries, and also this year, that have now communicated this ambition to be at net zero in 2050 or 2060, or 2018 in some countries. So I think that is a very promising development. At the same time, this needs to be translated as well by credible policies, of course. But we are calculating now the impact of that, and which would mean that in the long term, if you would really implement these targets, you have closed the gap a bit further again.
Thank you. Simon is asking, is the 5-year stock-take interval too long, given we have 9 years and therefore only 2 stock-takes to get there?
Yeah, I think you're right. So more or less, we would need to be right on this stock-take, more or less, to be have a chance on the 1.5 degree target. I think in reality, things are a little bit less tied to the official process, and policymakers, especially presidents, or try to organize their own processes in parallel to the UNFCCC negotiations. So that might be a way that we can escape a bit this 5-year pattern, because the chance that we do it right now is probably also not that high. So yeah, I'm also not extremely hopeful that we would. I'm very hopeful on the well below 2. I'm not so sure that we need the 1.5, but yeah, it does require some flexibility compared to the official stocktake organization.
I'll have, we are running out of time now. Sorry, we have a few more questions here in the chat. So I can copy and paste into your email so you can answer later. Perhaps the last question. Are you fine going for the last question?
Yeah, no. I can also stay 10 minutes later if that's helpful.
Okay, that's great. So for those of you who can stay a bit later, I'll just continue with the questions. I think this is very interesting. I'll just go with the next question by Scott Matter. It's what assumptions around economic growth are built into the scenarios and models, and why? Yeah,
so what we did was first making these storylines, then we went into to the OECD and asked them to help elaborating these scenarios into economic storylines. They did it using their long-term growth model combined with the CGE. More or less, it means that the more optimistic scenarios have a slightly higher growth rate or comparable growth rate to the historical growth. The less optimistic ones are somewhat below the historical growth rate, but still show quite some future economic growth. I think the one of the lowest would be the Ssb3, which probably has a growth rate even below, above 1%. Historically, over the last 30 years, we have seen the world economy to grow by about 2.8%. Yeah, so all the scenarios are growth scenarios. One reason is that we wanted the scenarios to be, and that's a requirement from IPCC anyway, to be consistent with the literature. And in 2015, this would be the range of the literature that was out there, scientific literature. I think it's also consistent with what economists would assess as the likely future. There's a famous paper by Nordhaus where he did an enlistation of economists and asked them, what do you think would be the economic growth rate? And so this is driven by, for instance, assumptions on labor productivity and capital productivity. Yeah, there are obviously now also a strong movement of people that are interested in degrowth scenarios, and you might expect that integrated systems are going to assess those. Whether they all ever will become IPCC scenarios, I don't know.
Thank you. We have a question by Craig Bishop. Reforestation would take CO2 out of the atmosphere. Are there expectations playing a significant role in reducing CO2 methane concentrations? How big a role might they play?
Yeah, so they are part of this negative emissions that I was talking about. So in the scenarios, we do assume that reforestation plays a role. And so on the one hand, it can be really important, simply because these budgets are so small that even a few hundred gigatons of CO2 that potentially would be provided by reforestation on net might make a big difference. At the same time, compared to our need to reduce emissions compared to the baseline, the big story still is to decarbonize the energy system. That's the most important thing. But reforestation and afforestation, we also need to realize that there is an impact on the biogeochemicals part and the CO2, but also on the biophysical part. There is an albedo component to this, which means that not every place on Earth is as interesting for afforestation.
Thank you. Follow-up question, is land currently used for cattle changes to crops? How big a change would that make?
Yeah, so that's a big change. So I don't have the numbers directly at hand, so I have to guess a bit, but I think it might be even a far majority of the land at the moment for agriculture is used for animal husbandry, either directly as pasture or indirectly because it's the crops are used as feed. And so reducing meat consumption only back to, for instance, the levels that are recommended for health already would reduce the amount of land that we need for meat production quite a bit, and would make the agriculture system much more efficient in terms of land use as it currently is, which would first of all reduce the methane emissions associated with animal husbandry. It would secondly free up land, which could be used then potentially for either bioenergy or reforestation, and so it's a game changer if we are able to reduce meat consumption.
Thank you. So we have, I think it's the last question. Julia Blasser is asking, out of interest, are AMMs validated against the historical changes? What would you say are their largest uncertainties?
Yeah, so there's uncertainty, quite a lot of uncertainty, obviously, in those models. Yeah, we do calibrate against the history. So first of all, most of the concepts that are used to develop these models are based on what was historical observation. Also, in our model, for instance, we start actually modeling in 1970. We forced the model more or less to go from 1970 to 2020. But it does give insights for us into how well the processes in the model are able to reproduce historical trends. So yes, there's calibration, but it's not as strong or as important as for biophysical models. And for biophysical models, we know that the laws of the past are also going to be the natural laws of the future. In the socioeconomic models, you partly want a break in the future from history. And so some of the things that you've observed historically, like the relationship between meat consumption and income, where we see that historically, if income rises, meat consumption goes up. So that is something that you might want to potentially see different in the future. So for us, compared to historical trends can help us to understand, is the model able to reproduce these trends? And it can also give us insights on how challenging something would be compared to what happened historically, but it's not as strongly coupled that you can devalidate a model based on the historical calibration.
Thank you very much. Just a final one, Scott Powers is asking if you could please point him to a good reference that covers your key slides and windows of opportunity for 1.5 and 2 degrees Celsius. And I just want to remind everyone that this talk was recorded and will make available on our website as well. So yes, if you can point to a reference, that would be great.
Yes, feel free to drop me an email.
Yes,
I can also send something to the organizers.
Yes, thank you so much for this great presentation, and thanks for coming.
Welcome.
To the CLEX seminar series.
Thank you.